Okay, so we started from last time regarding just giving an introduction about the industrial minerals. So we continued up to the ways of these mineral deposits can be formed. Sorry. We continued up to how these deposits can be formed in terms of magmatic processes, right? Considering some tectonic situations. We call these situations as tectonic settings. Okay, all these situations can be termed as tectonic settings. So these tectonic settings are due to Earth's internal forces. That means Earth's dynamic forces. Okay, so these dynamic forces cause these magma to accumulate, flow and accumulate in different regions of the crust, where due to cooling and also as a result of assimilations, that means interactions with the host rock, they tend to form mineral deposits because of dissolution of metals in particular. Okay, copper, zinc, lead, metals are easily dissolved in this magma during these assimilations and also during these crystallizations, magmatic crystallizations. So these materials get deposited or precipitated later on as a result of cooling. In addition to that, we talked about the hydrothermal conditions as well, where the groundwater, either internal groundwater or the water available in the seafloor, ocean water, right? That penetrates into the Earth's crust, either continental crust or oceanic crust. But this happens mainly in the oceanic crust, actually, because there is ample amount of water which goes into the oceanic crust, and which and also the oceanic crust is thin compared to the continental crust. Okay, the oceanic crust is thin compared to the continental crust, so therefore the depth to which need the magma, the groundwater to flow, is shallow in the case of oceanic crust. So therefore ocean water easily get heated, and they, due to this magma, shallow magma chambers or shallow magma flows, they get heated, and due to this heated groundwater circulation within the crust, metals get dissolved in that groundwater. So that is what we call the hydrothermal solution. So that is no longer normal water. Therefore, it becomes hydrothermal water, right? That means heated groundwater, which is rich in metals solutions. So once they reach the upper levels again, because they circulate, right? Like this, they circulate, they go deeper, and then they tend to come up due to the pressure prevailing in the deeper regions. They are pushed up and they come up and gradually get cools. If some fractures are available in the rock layers, that means within the crust, they can get penetrated into those, and they can precipitate as metals near the surface, right? Because this dissolved solution. And also they can come up to the ocean floor and again pool and deposit as some mineral deposits in the on the surface of the crust. Even in the continental crust also they can deposit. Okay, so these hydrothermal vein deposits are direct result of heated groundwater. Okay, so heated groundwater dissolves the metals. That is the main point. And another one situation is there, I think I did not mention that time, that is the contact metamorphic zones. So here you can see the contact metamorphic zones. This one, contact metamorphic zone. That means some regions like here, places like here, it's not working. So anyway, yes, in this region, heated groundwater, contact metamorphic zones where the magma is in contact with the host rock get heated, right? They get heated, and some reactions are taking place in a process we call a metamorphism. We call it contact metamorphism, and there are some mineralogical changes happen. Reactions can take place if, particularly if there are some carbonate sediments here, carbonate rocks or carbonate sediments here around here, they get easily reacted and dissolved also due to this heat, because it's like limestone like thing. They can easily get reacted, dissolved in this region because of this magma heat, right? That is what we call the contact metamorphism, and in that region some deposits can be formed due to these metamorphic reactions. So these are called skarn type of deposits. Skarn, SKARN, skarn deposits, right? So that is also one way of forming mineral deposits, but this is not very common. It's sort of rare situations only you can find such kind of deposits, but still there is possibility for finding such minerals, industrial minerals as deposited in skarns as a huge scale, also some kilometer scale also. So these are the mechanisms where we can expect how metals or how metal deposits or industrial mineral deposits, because these metals we also consider as industrial minerals, right? Because they have industrial applications. So therefore, as long as these metals are concerned, we can consider them as also industrial minerals or industrial metals. So these are get deposited in such regions. So these are some more mechanisms where these ore deposits can be formed. Okay, so the point is metal rich. Water or metal rich solutions or metal rich magmas. Either any of those solutions, when they cool, they are able to precipitate or deposit mineral deposits or deposits. Okay, so those are the magmatic type of main types of magmatic and hydrothermal situations where most of the mineral deposits in the world are formed. I think more than 70% of Earth's deposits are related with magmatic processes and hydrothermal processes. Okay, so skarns are rare, as I mentioned, but hydrothermal and magmatic deposits are very common. Those are the mostly abundant types of mineral deposits, industrial mineral deposits. And this is an example where you can see ore deposit, a section of an ore deposit, a cross section. You can see these folded layers. So all these are rock layers. Okay, all these are rock layers. You can see these are folded. Right, there is some folding is taking place. So these mineral deposits or metals or whatever the ore deposits that we are talking about are found in between these layers, right? For example, here you can see some accumulation of gold, right? This is ore mineral. As ore mineral, what you have is a gold, right? So at the same time, so here you can see easily a layer extending, right? This is this is a gold containing layer. Okay, so in at either sides of these two gold layers, what you have is host rock. Okay, so here also you have a gold layer, and either side of the gold layer what you have is some host rock. This host rock is mainly in this situation. Okay, the host rock is mainly composed of quartz, right? Quartz is there, so we consider this quartz as Kang mineral, because it is less important in terms of this mineral deposit, right? Because our main target in this mineral is gold, right? But still you can find Kang mineral quartz, because this rock is there quartzite, and in between this gold layer you have some quartz minerals also. So gang minerals means the excess, or sorry, the other remaining minerals apart from the main ore mineral. Okay, so in this case, gold is the ore mineral, but quartz, like other quartz and maybe some other minerals also there, right? They are called gang minerals. So these are less important because they are not economically extractable. I mean, the quantity wise. In this case, the quantity wise, gold has a very huge amount, very huge concentration. But even if you have zinc here, maybe you have zinc also associated with this one. But zinc may be not economically extractable. I mean, even though you extract it, the effort you are putting for extraction of zinc may be a waste. Okay, because they are not in a big quantity. Even though zinc can be considered as an ore mineral, in this particular situation, zinc bearing mineral should be a gang mineral, because they are less concentration. Okay. Similarly, in a zinc bearing deposit like zinc sulfide, the sphalerite deposit, okay, gold can be there, but gold may be not in big quantity. So you can consider the gold as a gang metal, okay, gang metal or gang industrial mineral. But at that case, zinc or sphalerite is the ore mineral. So likewise, the less important minerals which are found in associated with an ore is called gang mineral, as I mentioned in the previous lecture also. Okay, so this is a very nice gold deposit. You can find similar deposits can be found in Africa, Southern Africa also, Ghana, Western Africa as well, Botswana like countries also. They have this type of deposits. Actually, you can see here these gold layers, gold bearing layers are associated with two other rock layers, right? So here you have the rock layer. See, just a minute. You have the rock layers here, right? So here one rock layer and here another rock layer below that. So that means in between these two yellow lines, gold has deposited. So that means this gold has reached the joint of these two rock layers, or in other words, the contact. Previously, there has been some fracture-like thing, right? Some crack-like thing. So along that crack, this gold has come or intruded. So that layer has later deformed. That's why you see this type of folding with the rock. With the rock, it must have deformed. So see here, these are deformed. But before deformation, there should have been some cracks in between, right? Like this, in between. So into that, this gold may have intruded. So original magma should have intruded into the cracks like this, cracks or contacts, right? So because these are weak zones, so into these weak zones, they get intruded, and later on they cool and crystallize, precipitate this gold bearing layer. So this is how these gold bearing layers are produced in between rocks. So that's why we say that always magma or any hydrothermal solution, they try to penetrate into weak zones. So they always try to penetrate into weak zones in rock layers, in the crust, so that later on, when they get cool, all these dissolved materials will be deposited. Okay, So this is a very, very nice example that you can understand this magmatic or deposit formation. So here theoretically we considered that they are moving here and there and depositing and like that, right? So this is how it happens in theoretical aspect, but you can see clearly how does that happen in the real situation also. Okay, so here this is a real situation where you can see a real ore mineral deposit. Is it clear?
Yes, sir.
Yes, sir.
Yeah. So always we have to see the field relations as well. That means, for example, here this folding has happened with the gold layer. You can clearly see that with the gold layer. That means the host rock has deformed, has changed. That is folded. We call it folding. Right? These are happening due to tectonic forces. And if any case, if in any case, after folding, like here, right? For example, here this is a fold axis, right? So either side of this, you have the fold, right? You have fold like this, and this line we can call fold axis. So always these fold axes make the rock along that weaker, a little bit more weaker than the surroundings. So in any case, if you had another magma solution or hydrothermal solution penetrating through this rock layer, rock unit, it can intrude into this region as well, right, later on. So you have one mineralization here, right? This is old mineralization, and a young mineralization can be expected here as well, right? So this type of situations we call a second generation of O. That means first O generation is here at the stage 1, and after that particular event, we call that tectonic event as the folding event, right? So we have a second mineralization as well, in case if we have, but here you don't see that one. I'm just taking as an example, right? Because this region is weak region, right? It can even form cracks, later cracks. So along that, you can have some hydrothermal solution penetrated, or some another magma came in that can also crystallize along there. So you can see here such mineral deposits will cross-cut. They will cross-cut the origin, the earlier deposit, earlier layers. So we call this second type of mineralization as post-tectonic mineralization. Post-tectonic. Tectonic means this folding event. Tectonic event is the folding event. Therefore, we have probably we may see another mineralization which you can refer as post-tectonic mineralization. The first one, since it has happened before the folding event, we can call it pre-tectonic. So you have two mineralizations in that case if you have, but not here, but I'm just drawing. The first one is pre-tectonic mineralization, and the second one is post-tectonic mineralization. Sometimes during this folding event also you can have some mineralization happen, right? Such scenarios are also there. Commonly observed, yes, in highly deformed terrains, we can observe such mineralizations as well. So such mineralization, if available, you can term it as syntectonic mineralization. So there are three types of mineralization. Mineralizations can be expected in a terrain: pre-tectonic, syntectonic, and post-tectonic. So pre-tectonic means always before the tectonic event. So that means the effect of the tectonic event has should have also affected the mineralization. The second one, syntectonic situation, that means at the same time when the tectonic event is happening, that means when the folding is taking place, there can be mineralization. So that is syntectonic mineralization. And the third one, post-tectonic mineralization, that means after the tectonic event, after a tectonic event, if mineralization happens, that is called post-tectonic mineralization. So likewise, in geologically, you can categorize, and also tectonically, you can categorize those mineralizations by observing their textural relationships with the host rock and other mineralogical alignments and such kind of features, right? So in detail, a geologist can, by detailed observations, a geologist can understand whether that is pre-tectonic, syntectonic, or post-tectonic mineralization. So that is also very important in exploration, because you will have to see the field relations as well. So that's why, in addition to a mining geologist, mining engineer, there must be a mining geologist or a field geologist or an resource geologist working in most of the mines in the world. So they have to do exploration. The investigations, field investigations before explorations as well, right? So mapping is very important. Geological mapping is very important. Therefore, because in some situations you have to find the correct direction of mining, right? For example, in this case, the ore deposit layer is almost horizontal, right? You can see horizontal layer. So to mine this layer, there are several ways you can think of. But before mining, there should be some exploratory investigations where we are trying to find the extension of this layer, right? Extension of this layer. So can anybody tell me what kind of a method or technique can be used to see the extension of these layers once you have a prospective area? Maybe magnetic survey or resistivity survey. You using those techniques, you identify a prospective area first of all, right? But later on, I mentioned that you have to find out the boundaries and to which direction these layers are extending likewise. So there should be some other techniques to be applied after recognizing the prospective area. So can anybody just guess one way of recognizing, because you can't see these things on the surface, right? If you see the all features in the surface, then it's easy. You can determine the boundaries. But since these are barren, right? Barren means you don't see them on the surface and they are underground. Right? You have to do the exploration, further exploration to find out. Yes. Anybody tell me?
Gravitational.
Sorry?
Gravitational.
No.
Drilling, sir?
Yes.
Core drilling.
Yes, very good. Core drilling. Yeah, gravitational method we have already used. That means we have found the prospective area. Now we know that in this particular area, there should be this mineral deposit, and maybe some with the help of field observations also, you know that, okay, this is gold deposit or this is zinc deposit or whatever, but you don't know yet the extension of those, right? Only the area you know, but the directions you don't know. Whether these layers are horizontal or vertical or angled or whatever the things, you might not know correctly using the previous methods. So we have to do a physical method, physical technique to find out the extension of these layers, whether they are angled or horizontal or vertical or whatever it is, right? For that, you have to do some exploratory drilling, right? Yes, correctly mentioned, directly core drillings. So you have to do some exploratory drill holes. You have to dig some drill holes. So in the area, you select some regions you suspect. Based on your result, you can suspect some places where you think of drilling and see, because you can extract the samples after drilling, and to see whether at which depth these layers are found, like that, right? Of course, depth can also be determined by the magnetic or seismic surveys, but the directions may be very difficult. I mean, the direction of layer extension, for example, this layer extension here angled, and this part it is a horizontal, right? But this is very small scale, right? And here again different angle, right? So like that, because of this falling only, right? But in some cases you may have the gold layer extended like this, right? Like this in a angle direction, right? There you don't see easily a way of extracting that. So for that purpose, you have to go for core drilling. You have to go for core drilling, and for core drilling, you can do drilling from place like here, and again some place like here. Okay, and another place maybe here. Like that, you can drill and see how deep, like that. But when you drill and try to get the sample, you get only very limited section here, limited part only, right? If you do the drilling vertically here, right, you can find the layer like this, right? So that means however much you drill vertically, you will get a very small fraction of the ore deposit only, right? But after this drilling, you may realize their depths are different, right? For example, here depth is different, and here if you had a borehole, you know the depth is shallow compared to this one, compared to the first one, and the next drill hole will be more deeper, right, than the previous one. So that means you should understand that from this hole to this hole, this length, this short length. In this case, it is short, but in the field it may be longer than that. There should be some layer extension in an angular way, right? So because of this depth difference, you can understand this layer is extending in an angular manner. So rather than drilling vertically, if somebody can propose, okay, so I have this depth difference, so therefore, shall we start drilling and see in a direction like this, right? In a direction like this. So you can start drilling. It might be longer, right? Drilling may be longer, but still you are able to extract a huge amount of ore along that direction, right? So in mineral deposits, these lengths may be some hundreds of meters or even kilometer scale. So therefore, the cost of drilling that you apply for angular drilling, you can recover definitely easily. You can recover rather than drilling numerous holes and get little amount of the resource, right? The cost wise, I think angular drilling will make much more profitable method, right? Even you don't have to go for this type of long angle drilling. You can drill up to here vertically, and then you can turn in the proper direction and do the excavation, right? That is also possible. So likewise, you have to plan your drilling in the exploration stage after doing some exploratory drill holes at the very beginning. Okay, so this is how people understand the drill directions. And also actually in structural geology, there are some methods called stereographic projections. Stereographic projections where we take the structural details, directions and all of these borehole drillings, and use those drillings to find out this correct direction, right? This angle, correct angle. If you lose the angle, then you will end up with the quartzite all, right? So there will be nothing to extract. So therefore, This angle is very important. This angle is very important. So such stereographic projection method can be used to exactly find the more appropriate direction to drill also, right? So structural geologists know that, and also economic geologists who are involved in this mineral exploration, they know how to apply those stereographic projection methods to find out the drilling directions. Okay. So anyway, this is just an introduction to some field techniques on identifying these layers, because some layers you have something like very long but angled, right? It might end up in the surface. They will be ending up at the surface. So with a steep angle, these mineral layers are extending. Right. In that case, we can start from the surface very easily, and then it can be extended long and long as much as possible, right? But drilling has a limitation, right? It can go only very few kilometers maximum, right? I mean, the currently available techniques, but still a few hundreds of meters means for a gold like resource, it will be very, very economical. So anyway, this type of techniques are used for drilling these ore deposits. But some people just start drilling without start exploration without having this type of exploratory borehole network. They just start drilling, excavating regionally, right? That means they will just excavate a huge region like this, right? A big region, they will excavate like this, right? They make a pit-like thing and excavate and remove the material, and then sort whatever the ore body which is available there. It depends, right? So these are called underground, open pit drilling, open pit excavation. So this, we will see some examples. So you can just start drilling like you are quarrying, right? Rock quarry like thing, right? Just without considering only the ore, you just excavate the whole region, and then as the next process, you start sorting what is the ore material or gold or whatever separation is the next step. So that technique is the one which is used widely because it costs less money than going for a exploratory drilling network method, right? So anyway, there are several ways of excavations, and we will see some impacts on these type of excavations when these industrial minerals are extracted later on. Okay, right. So another, in addition to those magmatic types, there is another way of formation of mineral deposits, especially gold, because gold is heavy. So these heavy minerals, heavy metals, can easily be deposited even gravitationally, right? So gravitational deposition of these minerals, when we have such deposit, we call it them placer deposit. Okay, placer deposits or placers, right? So placers means it's a kind of natural sorting of material during a river flow or something like that, river flow or even ocean currents, right? Because the heavier minerals are get separated. So it's kind of a winnowing action. What is winnowing? We try to winnow out some rice or paddy, right, to remove the stones and heavier materials during our processing of those paddy and rice, right? So like that. So it's we use a winnowing fan, right, and for that such purpose. But this is a natural winnowing process, which is happening due to the flow of a river, right? For example, here there may be potholes, right? Potholes, in mountains or in waterfalls. Always there are some holes generated or created on the rock layer where on which the water is falling down, right? So there can be potholes formed, and there, because of these heavy materials are brought by the river or the stream or the water flow, these heavy materials get deposited here because the water gets escaped from this pothole gradually, placing these materials at the base of the pothole, right? So there also you can have very small scale placer deposits. In addition, in channels, on the channel itself, river or whatever the channel itself, there can be deposition taking place when it gets widened, right? For example, when the channel is getting narrowed here in this region and then gets widened, right? So it's something like delta-like feature, right? If it is ocean, but this is not the ocean. So in this situation, energy release is taking place because this squeezed area, all the particles are under high energy status. But once it comes to the broader region, they want to release their energy and they lose energy. So the more heavier ones get deposited in these banks, right? So the heavier ones get deposited in these banks. So therefore, some placer deposits can be formed in such regions as well, right? When the water is flowing and the channel width gets abruptly changed. In such situations, you can have placer deposits generated. Even in this region, even in this place, you can have some placer deposits formed because the material which are brought from upstream are waiting here to enter this narrow region. But during waiting time, the more heavier ones get deposited in this region, right? So this is also happening, right? And when two streams are connecting, right? One is coming here and another one is coming here, right? So when they get connected, also some energy conversions are happening, and in the middle of this region, some island-like regions are formed with sand and other heavy materials. So the placer deposits are formed in such regions also, right? These are very big rivers like Indian or Chinese rivers, these deposits are also very huge, right? Some kilometer scale, very, very economical to explore. So therefore, these are very important situations, right? So in addition to those, when the streams or rivers are get bended, we call meandering, right? Meandering. So when they form some loops like things due to this meandering, in this curved region, again, the velocities are different in particles from this direction to this the other direction. Velocities are different, and this the edge gets the slower movements, and heavier minerals will get deposited in this region, in this area, right? So placer deposits are formed in such places also, inside the meanders, right? So these folds like features we call meanders. This process is called meandering of rivers. And at the end of the river, which is meeting the ocean, there you may see some delta also in this region, right? So if you have a delta, so then a lot of deltaic deposits can be formed in this region. And also in addition to that, at the coast, you can have heavy mineral deposited. For example, we have very, very nice such deposit in Sri Lanka. Where is that? Can anybody tell me? we have a very good coastal deposit as a placer deposit in Sri Lanka. Where is it? Sorry? Yes, very good. Ulmudi, yeah, in Trincomalee, near north of Trincomalee. Pulmude is a place where we have the coastal deposits of rutile, ilmenite, because of Mahavali River. Okay, so there you have huge beach deposits formed. Actually, it's not a delta deposit; it's a beach deposit, and there are a lot of materials deposited. Okay. So this type of places are also found where we consider them as a result of detrital sediments, right? Detrital sediments means the sediments which are brought by the rivers. Detrital sediments means the sediments which are brought by rivers and they get deposited at various locations where you see this huge accumulation of ore deposits, right? So this is a very common type of formation of economic deposits in India, Sri Lanka, China. You have a lot of this type of deposits. Okay, right. So any question up to this? Do you have any question?
Is the rutile deposit the originated from the hill country, or does it originated from the sea itself?
No. It's not the sea. It's coming from hill country. I mean, in uplands, right? Long distance transportation of these materials over millions of years, right? Millions of years time, because all the rocks in the highland part contains a lot of rutile and ilmenite in their rocks. So when they get eroded, they will accumulate. They are carried by the rivers and transported through this channel. Especially the Mahavali River carries a huge amount of sediment load. So these are get deposited in the beach, and they are not resulting from the beach itself. They are coming from the land, right? So the source is the land. So for India also, the rivers like Brahmaputra, Ganga, rivers carries huge amount of materials, and they get dumped in the ocean, near the ocean, and there are a lot of such deposits.
Thank you, sir.
Okay. So in addition to those, there is another tectonic event or tectonic situation we have to consider, the divergent zones. What are the divergent zones? I think we have already discussed about that a little bit earlier. Can anybody tell me what is a divergent zone?
When the tectonic plates are moving, if it moves away from each other, it's divergent.
Yes, that's right. So when the tectonic plates move away from each other, here you in this type of regions, you have a vacuum zone generated, and to this such vacuums from the asthenosphere, magma is flowing, right? Magma is flowing from the bottom. So there magma get dumped onto the ocean floor, which this area we call rift zone, because there is a crack-like thing because of this plate motion of two separate directions. And this magma produces rocks like basalts, and sometimes dikes. They are generating some dikes. That means when the magma goes into cracks, like these cracks, right? Into these cracks, when the magma intrudes, we call them dikes. So again, what you have is dissolved materials, like dissolved metals. they get deposited. In these regions, right? Specifically, these are mafic rocks, because under this tectonic situation, you have a lot of mafic magma coming out, right? The mafic magma means iron magnesium rich magma, and which such magma is able to dissolve a lot of heavy metals. So that is why these heavy metals are associated with mafic magma. So this basalt mean mafic magma. It's a blackish type magma, and forms the formed rocks are also very dark color, blackish color. Okay, and at the same time, hydrothermal waters also cause material to precipitate, and especially sulfides. Sulfides get precipitated because hydrothermal water, when they get penetrated into the crust from the ocean, they are having less amount of oxygen, because in the interior, the oxygen amount is less because you are going away from the atmosphere. So less amount of oxygen means oxidizing conditions are not favorable there. So they are always having reducing conditions, and these reducing conditions are favorable for sulfides. Sulfides like to have reducing conditions to form. So therefore, a lot of sulfides are formed in terms of as a result of this activity, this hydrothermal activity. So therefore, a lot of sulfides are formed, and these sulfides are the formed sulfides are also carried up by this magma, and this magma then deposits sulfides also as mineral deposits in the these rift zones. In ocean floors, there are a lot of sulfide formation that is happening as a result of magma dumping, as well as hydrothermal sulfide solutions. So this is very, very common in the ocean floor. So we call this melting, decompression melting, because when the plates are moving away from each other, you can see the plates are moving away from each other. What is happening is this area become low pressure region, right? That's why it's a vacuum-like area, right? This area becomes low pressure. So the high pressure regions are available in the depth. And when it comes to low pressure, we call decompression. That means decreasing pressure. So due to decrease of this pressure, this asthenosphere tends to form melts. So one way of melting is decreasing pressure of the material itself, right? The other way, as you know, heating, right? As much as you heat, something can get melted, right? But at the same time, it is possible to melt by decreasing the pressure also, right? So that is what we call the decompressional melting or decompression melting, right? That happens under mid-ocean ridges or divergent zones in the oceanic atmosphere. Okay, so that is happen. And also a special feature can be observed where this a lot of hydrothermal activities are taking place. We call black smoker areas. Black smoker areas means along these cracks, when the hydrothermal water or hydrothermal solutions are moving, these hydrothermal solutions which are rich in metals, dissolved metals, tend to expel all these materials as with the smoke. With the smoke means they just due to temperature drop, they like forms a smoky type of release of this material, this water, right? It's kind of from high pressure to low pressure release of hydrothermal solution, right? It's a kind of a smoky like thing appearance, and because of dissolved materials, the hydrothermal water is sort of misty like appearance, grayish appearance. So therefore that whole region looks like a very dark spring like area. So that is what you call the black smoker, and such regions are very much rich in metal deposits, because all these materials are dumped inside the ocean floor by these black smokers, right? So we will see some black smoker. You can see here this diagram where you see some smoke-like thing coming out, right? Actually, this is gases releasing with the dissolved material from the hydrothermal solution. That's why you see this as a smoke-like feature. Actually, it is really gaseous liquid ejecting from the interior, right? So these are called black smoker places, and it's like a spring-like region. So you see in a spring, when water is ejecting at high pressure, you will see like misty appearance, right? So that is the thing happening here. As a smoker, it's not real smoker, but it's hot water. It's hot water coming out in the cracks, from the cracks. So that can precipitate various ores, sulfides, because as I mentioned, sulfides are having favorable conditions at the interior bottom of the ocean floor because of less oxygen or reducing conditions, right? So this is one example of black smoker, and I think you have a camera here. This is a camera. Okay, so we will see real activity of a black smoker. This is the real image coming, video image coming from a black smoker. Is it clear for all this black smoking process?
Yes, sir.
Okay, so this is underground, under ocean floor, where you see these black smokers are coming out. So these will dissolve. I mean, because the water here is cold compared to the place where these black smokers were generated, right? So soon they will get cooled and precipitate whatever the material they brought from the interior, right? So this is like smoking volcano-like feature, but actually it is a hydrothermal activity taking place in the ocean bottom. So these regions are very, very rich in metals, manganese, zinc, lead, like metals are very rich in these regions in the ocean floor, right? So people can do mining even under ocean, under water. Right. Okay, so this is especially related with divergent zones. So these black smokers are coming from divergent zones. One more situation is there, as I mentioned at the last week's lecture also, the plume generation. Plume generation, plumes are coming from very deep part of the earth. So that means it's coming almost from the core mantle boundary. Okay, core mantle boundary, that means some 2,700 kilometers below. So they can come up as a huge magma body, right? So it starts to come up, right? It starts to come up, and when they come some tens of kilometers, they tend to form like head, some bigger mass, headed magma mass, right? So we call plume head. This plume head gradually go up, right? It goes up. It takes some millions of years to come up, right? Anyway, and then it hits the crust ultimately, right? It hits the crust here, ultimately giving a huge disaster. So it will make so many cracks, and all these continents will be fragmented, right? They will get fractured. At the same time, the cooling magma from the plume will cause some basalt-like rocks to form on the ocean floor, right? So the important feature is this magma is coming from very deep. That means actually they are coming from lower mantle, right? Lower mantle here, you know, the subduction, when subduction taking place, the crust, when subduction goes, right? Like here, when the subduction taking place, what's happening? The materials are brought into the deep interior, right? So at a certain point, I said this subducting slab gets broken, and one part sinks down. One part sinks down to the mantle. It can go fragmented into the mantle, right? The other part will come back to the surface. The other part will come back to the surface to some extent, right? It's an equilibrium process. So these tiny materials which are brought to the mantle, deep mantle, it takes some hundreds of millions years, some 400, 500 million years time. They recycle inside, and they get deposited probably at the very, very deep part of the mantle. From there onwards, there is no way for them to travel, right? They get deposited and accumulated, right? These are materials from the subducting slabs. So, you know, subducting slabs contain a lot of sediments, right? So these sediments normally do not survive because these temperatures are very high. But when they are rich in carbon, right, from in the subduction slab, this carbon get transformed into graphite in the midway. Maybe here you have graphite. Okay, so some of the graphite will be going back to the surface when the slab is moving upward due to fragmentation, but some of the graphites remain there, and they also go down into the mantle, right? Some part. So when it goes deeper and deeper, this graphite is not stable because the graphite, the structure is different. It's a flaky structure you have. It is not stable under high pressure conditions. Under low pressure conditions and high temperature conditions, graphite is stable. But when it comes to the higher pressure conditions, graphite is not stable, and when it goes more and more deeper levels, it converts into diamond. So diamond is available in the deep part of the mantle. So that means in the lower mantle, you have a lot of diamond, right? Many diamonds are there like that, right? Individual diamonds are formed in the lower mantle because of this material which are going down deep into the mantle. So these diamond which are abundantly available in the lower mantle can be carried by this plume magma. So this type of graphite diamond is taken up by the plume magma, and it is coming up to the surface, right? So you have a lot of diamond deposited in some regions in the shallow crust because of this rising magma which is coming from the very deep part of the mantle, from the lower mantle, right? From the upper mantle, normal melting, which you can find in this type of tectonic settings, like in the rift zones, mid-ocean rift zones, the depth, you know, it's very, very shallow, maybe 5 kilometer, 10 kilometer, very shallow depth. So there, graphite is still stable as graphite. So you don't see any diamond there. But when it goes to very deep part, some thousands of kilometers down, actually even when it passes 100 kilometers, there is possibility for graphite to convert into diamond, right? But when it goes deeper and deeper, it will be accumulating in the lower mantle, and later on, at some time, it will be carried up by this rising plume magma. Okay, so this is possible to have diamond formed. So this is the most feasible mechanism for diamond to form One is plume magma and the other one is kimberlite magma. There is another type of magma called kimberlite, Kimberlite, kimberlite magma, right? That is also very deep magma coming from, but not actually as deep as the plume magma, but still some hundreds or 200 kilometer deep, right? So that magma, when melting, is coming as kimberlites, but not now actually. Now no kimberlite magma is there. It happened in the early stages of the Earth's evolution, some 1,000 million years ago. But still, this magma depositions we can find in the Earth's surface, right? Either in the Earth's surface or in the deep, in the lower regions, lower crustal regions, right? Still, unexplored magma is there, which were deposited some thousands, some hundreds of million years ago during the early Earth's evolution. So those are the places where these African people, African countries, which they are mining for diamond, right? So you can find diamond in the very shallow regions now because of this kimberlite magma deposition. Actually, this diamond is very early stages of formation of diamond from graphite. So about 100 kilometers means that magma contains also diamond, right? But plume magma brings the very deep seated diamond to the floor. And sometimes when this subducted slab comes back, some of the regions here gets converted into a rock type called eclogite. Eclogite means high pressure metamorphic rock. So in this high pressure metamorphic rock, also some graphite have converted into diamond. So that diamond is coming out with this equilibrium slab, which is coming upward as a result of this isostasy. Right? This is called isostasy. That means the maintaining the balance between the slabs after breaking. Okay. So in places like Kyrgyzstan or Russia, there are such diamonds found in metamorphic rocks, but those are high pressure metamorphic rocks, which are called eclogites. But those diamonds are very tiny, sometimes some millimeter scale or some maximum. Very rarely you can find 1 centimeter diamond in such rocks, but very very small micrometer to millimeter scale diamonds are you can find in such rocks easily. High pressure metamorphic rocks, but those are not economically extractable. I mean, you can't make it a mine there, right? Because they are disseminated here and there, and it's not easy to accumulate or collect as a ore deposit. So therefore, we don't mine such rocks, but for petrologist or the geologist, they can observe such diamonds even in thin section when they prepare samples. Okay, so this plume magma is another setting where these mineral deposits or industrial minerals are formed. So this diamond is the most valuable material which you can get in ore scale due to kimberlites or plume magma generations. Is it clear?
Excuse me, sir. What is the difference between plume magma and the kimberlite?
Well, the difference is the kimberlite is early melting of the crust. So it is still, the early melting of the mantle. I mean, before the earth was much evolved. That means from the early stages of the Earth's differentiation, you know, the continental crust was formed, right? So this continental crust was formed from the mantle melting, from this upper mantle melting. But the early magma, which was rich in a lot of carbon bearing materials, so which were rich in such magma, that means the kimberlite magma, that indicates the earliest basalts which formed as a result of mantle melting. Unlike today's magma is very much differentiated. That means their chemistry is very much changed due to various plate tectonic activities. Now there are so much of plate tectonic activities are taking place, but at the Archean time, that means early stages of the Earth, there were no much vigorous plate tectonic activities happening. So that magma was rich in mafic materials compared to today's magma. So they were sort of rich in such minerals. So therefore they deposited this special kind of materials like diamonds. But still they came from very deep in the mantle, but not as deep as plume magmas. Plume magma is just bringing up the material, mainly the subducted materials which are dissolved in the deep part of the mantle. So that magma brings back to the surface all these subducted materials. So since the carbon was present as diamond, so they are brought diamond also into that. But it was just once in a 400 million years time. But the kimberlites were very frequent at the Archean, in the Archean or late Proterozoic times. So they were frequently depositing these kimberlitic magmas. So that's why there were a lot of diamonds which are available in Africa, where the plume magma is not available in Africa because the setting is different. The plume magma is available in some regions only, where this plume hits on the surface as a triple junction. So once this plume hits, all the plates get fragmented into 3 parts like this. So we call triple junction here. So it's a devastating situation, right? When a hotspot is coming, means everywhere this continental surface gets oceanic continental surface get fragmented and dispersed. A new ocean is generated here. The Pacific Ocean is generated because of such plume. So that's why Hawaiian Islands are available there as the newly formed product from the plume magma, right? So anyway, the mechanism is quite different. But this kimberlitic magma is now not available because now the mantle is different, so that they are unable to produce kimberlitic magma in the current situation because the magma in the mantle or the composition in the mantle is so different now.
Thank you, sir.
Okay, so that's the only difference there. Right. So this is about the diamond formation. So the mostly found diamonds in Africa are brought by kimberlitic magma some millions of years ago, which you can find now on the surface. And also you can find these diamonds in streams also now, because once they are dumped in the crust, when the streams are flowing like this, when the streams are flowing, they carry the diamond also in the streams because of erosion, because the diamond is available in the crust because of this kimberlitic magma deposition here, right? So these diamonds are brought by the rivers, and at different places you might see the diamond also deposited. In Africa you can see such situations. Okay, so regarding diamond, as I mentioned, subduction zones are the main places where diamond can be found. In addition to those plume and kimberlitic magmas. So here I mentioned eclogite, so that is the subduction zone. Because carbon is taken into the mantle, which is converted into graphite and then into diamond. Right. So, you know, plumes rise from depths far below diamond formation depths. So diamond formation depth is somewhere here, right? As I mentioned. So that's why you can find in eclogite some diamond, but still below that, all carbon is available as diamond, right? So diamond formation depth is somewhere here, but you know, the plume is starting very deep, okay, from here. So it is rising very deep part, far below the diamond formation depth. Right. So when the plume is coming, it brings up the diamond also into that. So these are normal convection, normal asthenospheric convections. Here, for example, mid-ocean ridge is here. So this is mid-Atlantic ridge, which does not produce any diamond there, but only the magma coming from deep part, like here, brings up diamond. That's very important, the depth to consider. So you see here, South Africa, they have faced the kimberlitic magma at the early parts of the Earth's history. That magma may have brought a lot of diamond up to the surface. It's not the plume, but the kimberlites. When the plume comes up, it will bring a separate set of diamonds onto the surface. So you can go for diamond exploration in this type of tectonic settings, in this type of regions. Okay, so we have again the kimberlite, which was a very old type of magma. So this magma was available from at least the middle of the Earth. So they deposit a lot of carbon as diamond in the crust, right? So sea mounds are produced as a result of kimberlite magma also. So anyway, there can be a lot of diamonds produced in such regions as well. And these produced materials, or the produced diamond, will be taken back to the mantle again by the subduction also. So that means in certain period of time, when the Earth's evolution is going on, these tectonic processes cause the formed diamond on the surface, I mean the broad diamond on the surface, to take them back to the depths again. This is a cyclic process, okay? So every 300-400 million years time, this cycle continues, okay? Subduction continues. So once you have diamond formed here, so this diamond, when it reaches 200 million years or so, should have gone to the subduction zone somewhere here, right? And if no one explored it, or no one excavated it, it will go back to the lower mantle again. So this is a cyclic process which is happening throughout the history. Okay. Right. So up to now, we were talking about the mineral deposits which are taking place on the interior of the Earth. That means at least inside the crust, right? Inside the crust or inside the mantle, right? Inside the crust or inside the mantle. That means underground. But there are possibilities for mineral deposits to form on the surface or near surface, right? On the surface or near surface, which we term as supergene, ore deposits. Which we term as supergene ore deposits. So that is happening sometimes as a result of a secondary process. As a secondary process, what is secondary process? Primary processes. We have been talking about primary processes so far. All these interior processes are primary processes, right? So that is mainly driven by mantle convection or magmatic flows or whatever such mechanisms. Okay. So secondary processes means due to some effects of the climate or atmosphere or rainfall or whatever like that. So because of such secondary processes, the metals can be accumulated as a result of dissolving when the groundwater penetrates into the horizon, soil horizon, right? So materials are leached out. So we call them leached out, leaching, okay? And also oxidized as a result of oxidation, materials get dissolved and they get leached down to the deep part of the horizon, so the soil horizon, okay? And they get enriched in the bottom layers, and they get deposited as metal deposits. Near the groundwater table, sometimes they get deposited. Right? So these deposits we call supergene ore deposits. So these are secondary processes, right? And there is no magma involved here, no tectonic forces involved here, no convection, nothing, right? Only the climatic conditions or the atmospheric conditions, rainfall, such type of mechanisms helped to leach out these materials from the already existing rocks. So such deposits are called supergene ore deposits, and those mineral deposits, one example is bauxite. So what is bauxite? Has anybody learned about bauxite?
Aluminium ore?
Yes, it's an aluminium ore. Bauxite is aluminium ore. That means alumina, right? We extract aluminium from bauxite, right? So no much magmatic aluminium is available. Aluminium is not deposited as primary magmatic deposits. It's always secondary or supergene type of ore deposit. Bauxite, laterite, the places like Kalutara, there are a lot of laterite deposits, right? Iron ferric deposits, right? So such deposits are supergene ore deposits. So mainly the metals precipitated at or near the groundwater table. That means close to the surface. On the surface also sometimes you might see some depositions like Panirendawa iron deposit, like, right? All these are supergene ore deposits. Okay. So you can see one cross section here. This is an aluminium ore plus you have some iron. This reddish material is iron, and aluminium is this yellowish material. It's actually a mixed type. Bauxite is not just alumina. It contains other materials like laterite also, right? So laterite is also here. And another composition is gibbsite. Gibbsite deposits can also be found related with the bauxite deposit. That is aluminium hydroxide, right? Bauxite is aluminium oxide. So all these deposits are secondary deposits, right? As a result of water interaction, these hydroxides are formed like that. Okay, so ferric gives a reddish appearance to these deposits. So these are supergene near surface depositions, which we call supergene deposit. That is purely concentration of some metals as a result of secondary processes. And also weathering causes these supergene ore deposits to form. So here you see the weathering conditions. Weathering conditions are important. For example, this example from US, where you see the supergene ore deposits are formed. And as you know, when the sulfide minerals, like the materials which we talked about, the deposits which are formed in the Earth's interior as a result of magmatic processes, right, primary processes, these sulfides are taken to the surface, right, in places in different ways. You can see the formed sulfides are coming up to the surface with the magma or then deposited close to the surface. But you know, these sulfides are, they prefer anoxic conditions, as I mentioned, right? Because in the surface or near surface conditions, a lot of oxygen is there. So they do not prefer this, environment. They always prefer reducing conditions. So therefore, they are not stable under Earth's surface, right? They are not surface stable. So therefore, they just break down during weathering into iron, right? Metallic ions. For example, copper sulfide, lead sulfide, zinc sulfide, like components are broken down, forming ionic correspondent ionic material. Okay, so these ionic materials will be deposited as either oxides or carbonates or sulfates, because those are oxidizing conditions are available. For example, sulfide converts into sulfates also. That is also possible in the oxidizing conditions, right? So then they form leached, they get leached from the surface due to this water activity or the percolating water activity, and concentrate into secondary deposits, secondary copper deposits, secondary lead deposits, or secondary zinc deposits, right? So they form secondary type of deposits or supergene type of deposits, which are different from primary copper or primary lead zinc deposits, which we talked previously. Okay. So, but the metal is metal, so still you can extract them from either. It doesn't matter whether it is secondary or primary. But the thing is, in the secondary deposits, you have a lot of other ions as well, right? Because they are just a result of leaching, right? So everything gets leached in a secondary deposit. That's why you have laterite, bauxite, gibbsite, everything together as a mixture, right? But in the primary deposits, mostly you have a solid ore mineral. Of course, there are gangue minerals, but you have a very much, very well concentrated primary mineral there, right? So a lot of, you know, copper react with water, as mentioned, in supergene deposits. And therefore, you have a lot of copper deposits which are leaching out from the soil, came from the copper sulfides, initial copper sulfides. Now they convert into copper hydroxides or copper sulfates or other types during this leaching process due to weathering. Right. So these are the main types of ore deposits that we can find in the world, where we talked about primary ore deposits and secondary ore deposits. Okay. But as I mentioned, the most abundant types are the primary types, the magmatic types, plus hydrothermal. But the secondary or supergene ore deposits are not much available, and also they are not much pure also, right? They are not much pure as compared to the primary ore deposits. So we have secondary ore deposits like iron ore deposit in Panirendava. There you have iron deposit, and but the Seruvilla iron deposit is iron and copper deposit is not a secondary deposit. It's a primary deposit. It's associated with ultramafic rocks. That means there is a magmatic and hydrothermal evidence found in Seruvilla deposit. Maybe I will forward you some papers which were published on that deposit, and you can find a similar type of deposits in elsewhere in the world also. It's called Kiruna type deposit. It's a special type of mineral deposit which there are several locations in the world. So there are some similarities for our Seruvilla copper iron deposit also to those Kiruna type deposits. I will share with you some publications on that later on. But Panirenda iron deposit is a purely a supergene type of deposit. And also in the world, although even we don't have such a deposit in Sri Lanka, but banded iron formations, BIFs, banded iron formation, those are also secondary type of iron deposits, right? BIF. So these were available like the Kimberlite's magma at the early stages of the Earth's evolution, BIFs, not now. Long time ago, these banded iron formations were available in the Archean and Proterozoic times in the world. Right. Any questions regarding these primary and secondary deposits? Today, actually, last time also I forgot to mention you that to type your names and or numbers in the chat box. Can you please do that? Last time I think you did not do, right?
No, sir.
Yeah, please do that because attendance should be marked as the requirement for the PGIS. So therefore, please put your numbers or names in the chat box. Yeah, while doing that, you can ask the questions if you have any.
When we are talking the primary and the secondary deposit, most of the time the examples are the transition metals. So won't it be group 1, group 2 metals?
Well, group 1, group 2 metals we don't see as mineral deposits. That you mean alkaline metals, right? Sodium, potassium, like?
Yes, sir.
Yeah, actually, those are. Those are very much locked in rocks, in rock forming minerals. You know, so the minerals like feldspar, quartz, amphibole, pyroxene, every mineral contain sodium, potassium, calcium like elements abundantly. So we don't see them as mineral deposits found anywhere in the world. So if you want to extract potassium, then you have to go for extracting minerals like mica, right? Because mica contains a lot of potassium. But you don't find any deposition of such alkaline elements in a deposit, in an ore deposit, like, because they are very reactive, as you know. So they get easily accommodated into minerals and they get locked in the mineral structure. Therefore, there is no such materials available to form as a dissolved material in magmatic solutions or hydrothermal solutions. So the transition metals, you don't see them very reactive, but they can be abundantly found and dissolved into the magmatic fluids or hydrothermal fluids. Therefore, right, they are not accommodated in minerals much.
Thank you, sir. So how about, sir, in the transition metal, like if the group elements?
Which group elements?
Rare earth elements, would it be like the group 1, 2 elements or like transition elements?
Yeah, rare earth elements are also not accommodated into mineral structures. Okay, but rare minerals like the what we call ore minerals, what economic minerals, for example, monazite, right? Monazite contains a lot of rare earth elements. So if you such monazite, badylite, zircon, they contains a lot of rare earth elements, and they get concentrated in such such minerals, and they get deposited as mineral deposit, not as rare earth element deposits. So rare earth element deposits we rarely find, but we find rare mineral deposits like uraninite for uranium, monazite for lanthanum, cerium, yttrium, elements. Likewise.
Thank you, sir.
Yeah. Even garnet can contain some rare earth elements. Yeah. It all depends on the affinity of such elements into the mineral phases. Have you typed your names? 1, 2, 3. Only 3 is there. One more is there, right? So you can just type your name if you did not do. Okay. Right. So we will. We have still some time, so therefore we can move to the. Another section that is regarding mine exploration and designing, and the aspects that we have to consider, and also which are influential in mining processes. Okay, so we will see that part as well. Right, mine exploration and development. So actually in this case we have to consider whether ore can be extracted economically. A mineral can be extracted economically, even though however much you have a mineral deposit extent wise. If it is non-extractable, that means if it is very difficult to extract, then that particular mineral cannot be considered as an ore deposit. Okay, for any, even if it is gold, at that instance it doesn't it doesn't get categorized into an ore deposit, right? If it is not extractable economically. So this economic extraction is very, very important. So here we define the size, shape, and grade of the ore body mainly. That means the extent wise, and also the grade wise, purity. Purity is also very important. Okay, so normally we give the grade as grams per ton value. Okay, it's something like grams per ton. Like for example, if you have gold, 5 grams of if you have gold, 5 grams of gold per metric ton, right? Metric ton is 10 to the power 6 grams, right? So how many grams you can extract from 10 to the power 6 grams of ore? That means 1 million grams of ore, the whole mass. Out of that, how much gold you can find? So normally that gives the grade, right? So if it is 5 grams from the metric ton you can extract, it gives the grade as 5 into 10 to the power minus 6, right? So it's just giving a number only, considering the purity, the amount you can extract. For example, if you have an aluminum ore, if it is 400 kilograms of aluminum per metric ton, then the grade will be 0.4, right? 400 divided by 10 to the power 6 grams. 400, no, it should be in grams, right? 400 into 10 to the power 3 divided by 10 to the power 6. It's 0.4. So that is the grade. Normally, that is how the mass of the commodity per mass of ore. That is how you define the grade. So normally we use drill cores, right? You can first that's why I mentioned that we have to do some exploratory drilling network to find out the amounts of material that you can extract. So maybe you depending on the extent, you make 50, 100 or something, 50, 60 or 100 or something like that drill hole numbers, and take out the samples and give an average value or something like that, right? So that is, although expensive, that is the mostly used way of grading. Or otherwise, if you do the mass excavations like open pit mining, then you can get the sample, and then you have to calculate it accordingly, right? That will give you the extent of ore. That is the grade. The mass of the commodity is important. So while designing a plan for the mining, because you must have a profitable plan, otherwise this mining activity or the mineral resource extraction doesn't work, right? Because you have to consider so many facts, not only the profit, but also maintaining the activity for many years, because it takes long time, right? Sometimes tens of years or hundreds of years in some cases. Some historical mines are there in the world, right? Even ours we have, right? For decades, some few decades, we have been mining some places like Eppavala, Bogala graphite, Eppavala phosphate, Seruvila even, right? So for decades we are mining. So therefore, there should be a very well planned methodology for that, right? So first you have to analyze the requirements to start up mining, right? That is that must be done by the miner. And capital, transportation, labor cost, cost of processing, etc. You have to consider for many years ahead. Then it has to be complying with the governmental regulations as well. So that means initially you may need to get license, permissions, and the feasibilities, everything you have to get. And for that also you have to plan ahead of excavations. And also most important factor nowadays is the mitigating environmental damage. Definitely there will be damage to the environment. So therefore you can't avoid that anyway, but you have to mitigate it. That is important. Mitigating means you have to regularize the damage or to minimize the damage. And also if the damage is there, then you have to compensate that also by refilling or forestation or whatever the method that you have to apply, recommended method. And also the strategies for making profitability in changing marketplace. You know, we are mining for 10 years, for example. At the time of starting the mine, you have a plan considering the current market value. But when it comes to 5 years, the economy totally change. Maybe the today's situation, right? It's very different from 2015, right? So now you have to readjust your plan because otherwise you will not get any profit, or you cannot do the activity as expected. So therefore, such all the things have to be considered. And also, if you have a proper investigation of the mine, proper geological investigation, then you must have a cross-section produced by your exploration geologist, right? So for example, if your area is something like this slide, right, where you see different gold mineralization, right, in different places, right? So you see, these are the places where you did some drilling. You did some drilling and found the exploration, and also you calculated the grade also, right? So at different places, you see different profitable, I mean, different amounts of grades are there, right? So therefore, you have to go for the most economical way of finding such concentrations, right? If it is too low, then there is no point of excavating in that direction. Although if you have a huge concentration, but if it is very deep, like here, if it is very deep, so then still it might not be economical to go, right? So therefore, it's very, very important that this is an hypothetical case anyway, from an Australian mine. But it's better if you can do this type of a proper plan, proper scientific plan or method at the very beginning. And also, if you don't have enough money for investing such type of a method, then what you have to do is you just go for open pit mining, right? So you select some region and start mining. But you see here, a huge amount of ore burden has to be removed first of all. Before you finding the ore deposit, you have to remove all this ore burden. Then only you find this region, right? Still, it's very costly, but maybe less costly than going for a drilling network, because drilling is very, very expensive. Only big companies can do that. So anyway, depending on the situation, you have to do a proper plan. Otherwise, it's very, very difficult for carrying out. So appropriate mining techniques is the main important part of that, right? And so we have different types of mining, as I mentioned before, considering the cost as well. So the surface mining is the first type, where we consider just scooping off the surface of the earth, as I mentioned here, just open pit mining like, right? So it's cheap. It might be cheap or cheaper than the other methods, and safe also for miners. Why? You are just excavating openly, right? You're just removing the open area, and you have the working area here. It's not like mining inside here, where you are mining in a tunnel or underground, right? It's not safe. But open mining is, surface mining or open mining is just very safe for miners, for workers. You have to think of the workers also, their health, their welfare, everything. You have to maintain that. Otherwise, you can't sustain the industry. And also, you have a large environmental destruction. That's the problem, right? So you have huge area where you are destroying the environment. And also, if you want to compensate the damage, you have to spend a huge amount of money also for refilling this area, and forestation or reforestation, whatever the aspects that you have to do, it will be very, very costly. So therefore, it's not an easy task for this one. Whereas if you consider the underground mining, there you have to use adits or tunnels or shafts, right, to reach deeply buried ores, right? Something like here, you have to find a shaft or some tunnel or adit or some ways, because you can't keep on mining huge lengths, drilling huge lengths like that in angle way. But you can drill like this. If you want to go for an economical way, you drill vertically up to here, which is a little bit cheaper. Then you go angular way to extract this much, right? So likewise, you can select adits or shafts to reach the deeply buried ores, but it's expensive, right? It's expensive and also hazardous for miners too. It's hazardous. That means it's dangerous for the employees. And the good thing is it has less environmental damage because we are not destroying everywhere. So therefore, you have a less environmental damage. So both pros and cons have to be considered when you go for mining, right? So it is just at the very beginning, you have to decide what to do, right? Otherwise, it will be a waste of your investment, and also it will be just a damage to the environment, right? So if we consider surface mining, again, we have the open pit mining, as I mentioned, where what we do is a funnel shaped hole is excavated on the ground, right? It's something like this. So open pit here, it's being excavated as in a shape of a funnel, right? So keep on removing the material because for stability, you can't go in opposite direction, right? You can't go like this. It will collapse, right? This part will collapse when you go deeper and deeper. So therefore, you have to go for opposite direction. So it can be spiraling down along sides. That means from like this, right? From sides, you can go, right? In a circular direction, right? So this is an example of zinc ore in US, right? They are doing open pit mine. So you see here spiraling like layers. See, so this is circular. It goes all the way like this and come up. Then next cycle like that. So it's a spiraling like this. Okay. So it's an open pit mining way. And the other one is strip mining. So the other one is strip mining. It's you just blast and then scoop the rock and the overburden, right? So then take out the material and in strip wise, like strips, right? Partly you do that, part by part. So this is an aluminum mine. So in US, so you see the strip mining is taking place, but it is open surface anyway. So it's not very deep. It's not going deep like in a funnel-like thing in the previous situation, right? It's shallow, but extensive. Large land area is involved. So for coal and bauxite, it's recommended, I think. The reason is coal, you know, it's a very horizontal or very extensive, right? Not horizontal. It's almost, yeah, it's almost horizontal, but not very thick, like in gold mines. Like, so therefore, you can go for a large area to find the deposits. Right? It's a sheet-like thing. Coal. See, we call seam. Coal seam. That's why we call them coal seam. So here, see, this is coal seam, right? It's a sheet-like thing. So you can go for surface type of mining. Okay, so this is a coal mining. It's all an industrial carbon. And if you consider the underground mining, because this is surface mining, so the open pit and strip mining, if you compare it with the underground mining, where we do tunneling or adits, right? It's very dangerous because you have a roof here, and there can be collapse, and also some accidents when people can fall down when they work in such regions, right? So that's where, and also it's very dark. You can't see also, and you need lighting. and no oxygen, I mean less oxygen, that's very, very dangerous, right? So anyway, it depends on the resource you have and the depth you have. You have to select the method. So especially when the ore deposit is steep, you have to go for that. And also if it is steep, again, you have to go for the same thing. And also the grade is high enough to exceed the costs. So that's why I mentioned at the very beginning. The grade is important. If it is less, I mean, less purity, even though it's deep mining, it's not economical. Even though the grade is very high, but very, very deep, then still it's not good to mine. So it does not become a ore deposit, economic mineral deposit, right? So otherwise, you can't exceed the costs. So that is another situation. You have to bring the vehicles inside, right? For that, you have to make paths in tunnels up to the surface, and it's very, very dangerous, right? So anyway, modern mines, many safety standards are utilized, right? So large companies do this, otherwise it cannot be afforded, right? So you have to stabilize the roofs, you have to stabilize all these tunnels, right? You have to give supports, right? And when you excavate, then you have to support the area, right? Likewise, little by little, you have to plan it, and also you have to plan in a very, very suitable way, considering the structures, rock structures also, right? So you cannot continue. Maybe you can branch it out, right? Just to maintain the stability of the area, right? And also recoverable and profitable quantities should be there. Otherwise, it will not be feasible. Okay, so then we move to beneficiation, where the benefit, how this can be benefited. That means the separation of the ore mineral from waste material. So however much you excavated the material, if you can't them separate, I mean, if you can't separate them out from the gangue minerals or other impurities, right? Then it's a problem. So therefore, you have to find means of separation of material once you excavate it, right? It's not the 100% pure thing you are excavating, right? You have to have a mechanism to separate. But in the case of Bogala, the mine that we have been doing, right? You know, our graphite is very pure, right? Purity is very high. So most of the mass you are excavating in Bogala doesn't need to be separate methods to separation, right? That means it's pure, it's coming as pure graphite, right? So that is very, very good for us, but actually that benefit goes to some other country. I mean, we are not, I mean, the Sri Lanka is not operating the total company, right? It's a German joint venture, so they get the whole benefit of that anyway. So for this type of separation, you have to go for bench testing, the quality testing, treatment processes required to separate out the unnecessary materials, right? So all these things have to become considered under beneficiation part. So the mining does not stop at just excavation, right? So there should be a way for beneficiation as well. Okay, so the separation is very, very important. So sometimes you might need to refine the material, need to be refined. For that, so probably you may have to use a milling milling technique. That means you have to crush or grind the material, and then maybe you have to sieve or flotation technique to remove the material depending on the density or the chemistry or whatever, right? So whatever the separation method, you have to go for a plan for separating the material as well. Okay, so this is very, very important. So for this also you need to have a huge setup installed on the surface, because the material should be taken to the surface as well. To do this, it's doing underground is very difficult. Some mines might be doing that also, but it's safe to do and economical to do on the underground. But in that case, you have to plan the methods of transporting the materials to the surface. And dumping out the unwanted materials after separation is another problem. Sometimes people, that's why they used to try to separate them underground, so that you can leave the unwanted materials there, so that you don't have to worry about their dumping later on, right? So that is such many complexities are there related with mining. Right. So several processes might be there, like as I mentioned, crushing, and then probably grinding also, right? Sometimes you can straight away go after crushing to this stage, but sometimes you have to do grinding as well, right? Crushing is just overall smashing the stuff, and the grinding is to make them into more smaller particles. And then if you are using a wet method, you can do flotation depending on the material that you are mining, right? If it is density separatable, so you can do a flotation method, so that heavier ones sink and tailings can be separated safely. And then you have to do dewatering, or if it is a heavy liquid used, heavy liquid means high density liquids are also used for separation, right? For example, if it is a zircon monazite like thing, you have to use a heavy liquid, so that because the water cannot be used, because everything sinks in water. Even quartz is sinking in water, so therefore you have to use a heavy liquid. That means a high density liquid, so that many even quartz like heavy materials which are sinking in water will float in that particular liquid. But the more high density material like zircon, rutile like things will sink. So now you can separate them out easily. So likewise, there can be different separation ways, right? So you might need to dewater or liquidize the mixture, so that you can get another set of tailings here, so separately. And probably you may need to filter also, right? And then drying, and later on you might need to send it to a smelter also. That means melting, right? For separation. Iron, for example, you have to do melting, then only you can separate pure iron out of that from the soil. So likewise, there may be a lot of complications, and depending on the material that you are exploring, you have to find a method to separate the thing. Everything cost. So therefore, you have to do a well-planned design at the very beginning. That's why I mentioned at the time of thinking of exploration, you have to plan everything. Right. So here, another example where they are loading the materials to transport, because the excavated material is here. It's being transported to another place for separation to remove the unnecessary stuff or the impurities. So this is a whole complicated process, and this is an example of crushing. And once crushed, the crushed materials are accumulated here, and they can be further treated like we did here, right? After crushing, grinding or flotation or whatever the techniques that you have to follow can be proceeded. Okay, so huge setup has to be made in the mining location. So this is a mill, ball mill. So further crushing, further grinding, you can do using a ball mill. This is a huge ball mill. Ball mill means there are materials like agate, right? Crystals, right? Agate, so aluminum nitride or artificial crystals, artificial materials. So you have huge amount of balls inside at different sizes, maybe, or in same size. They get collided with the material, and inside this, your ore material get crushed inside. So that means they get ground. They get ground. Grinding is taking place by moving balls like this. So they hit with the sample and get crushed. So this is the ball mill. Sometimes it's used agate. You know agate, feldspar. It's also a gem, right? But not gem quality. But the balls are there, made of agate materials, right? And also for this type of huge industries, you don't have agate that in that big size. You have to do for commercial, I mean artificial type, aluminum nitride, silicon carbide, like materials. And then flotation is taking place in some cases, as I mentioned. So the lighter ones get floated, right? Lighter ones, lighter materials are floating here, and heavier ones sink down to the liquid, and this liquid can separately collected and treated to separate out those heavy materials. The lighter ones, if you need, you can collect, or otherwise you can dump them out. It's a one stage of separation. It's a flotation method. So some people have to use a heavy liquid for this instead of water. But in that case, it will be very, very expensive, because you can't go for huge tanks like this. But you may have tiny tanks like barrels like thing. And individually, in those barrels, this flotation is taking place, right? So one barrel to another. Right, so the floating, so you can collect the material accumulated down at different scales. And this is an example of dewaterizing. I'm not very sure how they do it, but you can see several tanks here, right? From one tank to another, maybe they are moving gradually to separate the water out, I think. Right, this is, I think, in US, this dewatering plant is taking place. So they have, I think, they have made it at the pit itself, at the location itself, right? So that will cut the cost of transporting materials, etc. Right? See, this is the open pit mined areas. So after that, finally, what you have to do is refining, right? Refining is very important, because in some materials you need refining. Some materials might not need refining process. They can straight away, after the previous steps, they can straight away taken to the market. But in some cases, some material needs smelting, right? Smelting. So it removes the metal from the ore mineral, right? Because some materials are bonded with the mineral in the ore. Whatever the mechanical process separation method, that these are mechanical separation methods. Okay, these methods might not be effective for separation. So therefore, they may need smelting to remove the real metal iron, right? Some cases, most of the cases, this ore will be heated with a flux, right? Flux means some extra materials you add so that you can decrease the melting point of the material. As you know, to melt some materials, you need to heat up to 800 degrees Celsius light, right? So that is also very costly to find such high temperatures by Mappal furnace or whatever. So it's not easy to heat like that. So in that case, you can use flux into that, so that the melting point get decreased, right? So melting point get decreased, so that at a low temperature it can be melted, right? So this has happened in some plants. So borates, lithium metaborate like compounds are used for this purpose. Usually borates are able to act as a flux, lithium metaborate like thing. And leaching, heap leaching, that means the heap of material lets to leach the materials. So that also removes the metal from its ore by reaction with the solution. It's almost same as the secondary natural process of secondary ore deposit formation, supergene deposit formation, right? So like that. It's very, very important, this process to go in. So this is one place where this melting is taking place. Iron hematite, you know, ferric oxide. Hematite is being heated and melted. Right. But this is very expensive and costs energy also. Right. So from banded iron formations, BIFs, materials are taken up and smelted to extract iron. Sometimes you have to use coke, carbon from coal, where carbon from coal is also taken in that way. In a furnace, this is happening in a furnace. So this is a furnace for that purpose, special kind of a furnace. Okay, most of the cases, the reactions are taking place is some gaseous formations because under anoxic conditions or oxic conditions, both conditions can be used depending on the requirement. Okay, so once this melting is taking place, the forming melt is immiscible. So that does not mix with iron melt. The silicate melt is immiscible. So you can remove the iron melt separately, easily. So that is why this type of melting is taking place, smelting processes are taking place, right? So this immiscible liquid goes to the bottom of the furnace. So here, once it's formed, it penetrates down to the furnace. So from there, you can take it out. So because of immiscibility, so they are not getting mixed together. It's like oil and water, right? Immiscible melts. So that's the reason. So this type of very expensive ways are expensive methods are used. For example, one more reaction is here: carbon monoxide forming reaction, hematite, magnetite. So these are the ways of the methods of smelting, and there is some reactions which are taking place in the smelting processes. Okay, right. Some more complicated methods are also used in smelting reactions. For example, aluminum hydroxide or bauxite, gibbsite precipitations, gibbsite productions, they mix bauxite with water, right? So that hydroxides are formed at high temperature, and they dissolve the aluminum, right? See, that dissolves aluminum out of that, and some then some residue is left behind. So then you cool the solution so that aluminum hydroxide or gibbsite gets precipitated because of from bauxite it comes out. So later on, this aluminum hydroxide, the formed aluminum hydroxide is oxidized in a furnace. You heat it under oxidizing conditions so that it will convert into aluminum oxide, right? So then this alumina is dissolved in molten flux again, just to act as a flux here, sodium aluminum fluoride. It makes acting with the carbon anode, carbon electric conducting material. Alumina, when they react, when the low voltage electricity is passing through, aluminum is precipitated, right? It's like in a gold or in a jewelry, people replate the gold, right? Using some sulfuric acid and 2 electrodes. So something like that. Copper also can be plated like that. So it's a separation method again. So this aluminum melt is immiscible, so that can be separated out. So these are very, very sophisticated industrial methods where these metals are get separated. Okay. So these are the main types of refineries or refining ways for ores to be considered as marketable products, right? To bring them into the market, you have to follow all these types of methods. Actually, depending on whatever the resource, you have to consider the way of refining. Okay. So I think for today we can stop here because we have discussed quite a lot amount of material. If you have any question, you can just ask me now. Because planning is very important before exploration, right? Because this is a very expensive job. That's the thing. It's not like just quarrying a limestone quarry or something like that. Ore mineral extraction is very complicated. That's why in Sri Lanka, people just export the materials at raw. The materials at raw, they export because of these complications. When you want to purify the materials, right? Even rutile, we export at raw without extracting titanium, right? That's the thing. Okay, if you have any question.